Hello everyone. I would like first of all to thank the organizers of this meeting for inviting me here today to present the work Geoscience Australia is undertaking to advance our understanding of Australia's geological architecture. Before I start, I would also like to acknowledge my colleagues at Geoscience Australia and many key partners who contribute greatly to this work. As we know, subsurface holds vital resources for industries and opportunities to decarbonize our economy. So building the most accurate picture of the subsurface is fundamental to refine our predictions of resource potential. But very little is known undercover, and the foundational work is required to gain better knowledge of the subsurface. On this map, for example, you can see a clear correlation between the location of major mines and known deposits, shown as purple dots, and the outcropping bedrock shown in dark colors. There are only limited discoveries in covered regions, shown in yellow-green pale colors. However, there are lots of proxies we can use to map the subsurface geology and support new discoveries, for example, using magnetic data. We can draw from this new knowledge to identify regions with mineral resources potential, for example, the shallow covered basement and sedimentary basins that are important source of critical minerals. In the next 15 minutes, I will present you the approach we adopted at GA to map geology undercover. This work is undertaken under the Exploring for the Future program. It's a $225 million program funded by the Australian government that started in 2016 in Northern Australia. It has been extended and expanded since 2020. The program was designed to develop an integrated geoscientific understanding of mineral energy and groundwater potential in Australia to support more diverse exploration investment and increase Australia's attractiveness as an exploration destination. The 2020 to 2024 program is currently focused on 8 interrelated projects aiming to grow our understanding of subsurface geology. They include 3 deep dive projects, 3 continental scale projects with a focus on Southern Australia, and 2 program support projects. One of the national scale projects, the Australia's Resources Framework project, aims to provide the ability to assess resource potential on any part of Australia. And to achieve this goal, this project will deliver the foundations for a national scale view of Australia's subsurface that will be refined through regional studies. If we focus on mineral potential, we know that to better map the signature of mineral systems, we need to take into account all geological factors that control the generation and preservation of mineral deposits. So, to produce a robust, predictive mineral potential models, we need to have a good understanding of the geological architecture and tectonic evolution, but we also need to identify geochemical and geophysical signatures. The National Geological Framework, the National Geochemical Framework, and the National Mineral Potential are the 3 main topics covered by the project. These activities are supported by national-scale pre-competitive data acquisition programs, mapping activities, and big data analytics. The new geological knowledge and data infrastructure that is generated at national scale will contribute to improve our understanding of mineral systems and directly support the research undertaken under the Critical Minerals Mapping Initiative. So let's focus now on our approach to 3D cover modeling that paves the way towards a 3D geological model of Australia. The methodology that underpins 3D geological modeling is relatively simple. The very first and main step includes the compilation and enhancement of legacy data, interpretation, harmonization, and data creation. Then, this data needs to be stored in a consistent manner and with a comprehensive list of metadata to be meaningful. The step number 3 includes the design of modeling tools we will use to generate predictive datasets that will feed into the 3D model. At Geoscience Australia, we are using 2 modeling approaches. We developed a machine learning pipeline called UncoverML, and together with many other partners, including the US Geological Survey and the Geological Survey of Canada, we also contribute to the development of the implicit 3D geological modeling platform, Loop 3D. From here, start an iterative process which requires to go back and forth between the data and the model to ensure a consistent interpretation. This is not a trivial process, but it's a very useful exercise that not only helps test and refine our geological understanding, but it also helps adjust what and how we capture data to maximize the potential. Finally, an important step is to ensure the data, workflows, and tools are all open source and respect the FAIR principle, so that model can be reproduced and updated at any time. Let's unpack a bit this workflow and go through the few key national scale datasets. So understanding mineral systems starts with good geology. So we have adopted a layered approach to map geology in space and time by integrating multidisciplinary and multi-scale data and move from this 2D traditional geology map to a layered model. And given the scale of the project, we only map the key chronostratigraphic surfaces that correspond to the base of geological eras. In 2020, we completed a seamless solid geology dataset across Northern Australia. This work consists of peeling off stratigraphic units layer by layer to reveal the extent and nature of all the rocks. These interpretive maps help predict the spatial distribution of stratigraphic units that can be prospective for minerals, energy, and groundwater, and in some cases, it can significantly expand exploration opportunities. This work is progressing very well, and to date, a first pass is available for most of the states in Australia, with work underway in Southern Australia and only limited regions in Queensland and Tasmania still to be covered. To complement this dataset, we are also in the process of finalizing a continental-wide metamorphic map that you can see here on the right. 48 orogenic cycles have been identified, spanning from the Paleoarchean to the Miocene. This dataset provides a basis for understanding the metamorphic evolution of all orogenic systems, provinces, and terrains, and will help determine whether optimal thermal conditions were met to activate the mineral system. Then, the next step is to assign a depth to these solid geology surfaces that will take us one step closer to a true 3D geological model. So under the Exploring for the Future program and in collaboration with the state and territory geological surveys, Geoscience Australia has been acquiring the world's largest airborne electromagnetic survey with 20-kilometer line spacing. This regional scale data is a very good proxy to map the geology undercover. For example, you can see regional scale features such as the resistive basement in dark blue and conductive sedimentary basins in warmer colors. Where we have infill data, we can map at a higher resolution and refine, for example, the geometry of paleovalleys. To date, we have completed a first pass interpretation in the area outlined by the yellow polygon, and work is in progress in Eastern Australia. But as you can imagine, given the size of the dataset, this is a very time-intensive process. So we have some semi-automated interpretation tools, including a module within UncoverML that are currently in development to assist with regional scale interpretation. So what does the interpretation look like? So in this line, you can see lateral and depth variations of the electrical conductivity. When the survey was designed, the flight lines were diverted to intersect locations of drill holes to facilitate the correlation between these conductivity changes and the stratigraphy from the drill holes and from the surface geology. The pink line here represents the limit of interpretation that goes down to 200 to 300 meters. From this interpretation, we were able to evaluate the spatial extent of sedimentary basins and map key horizons under cover. The resulting depth estimates were compiled in a new database called the Estimates of Geological and Geophysical Surfaces Database, or EGGS. The EGGS platform was designed to store consistent depth information from various datasets. To date, EGGS can store depth estimates picked from boreholes, magnetics and AEM data, and more data types are being added. Because EGGS is underpinned by other databases at GA, such as the borehole database and the Australian Stratigraphic Units database, it's dynamic and it can grow with an evolving geological framework. The database also allows to keep track of interpretation changes with a link to a survey specifications and processing file. And what type of information do we capture with this interpretation? Well, as mentioned before, given we work at continental scale, we only focus on mapping the depth to major age boundaries. We capture information about contact type and stratigraphic units, both above and below the boundary of interest. And all the stratigraphic information is based on the Australian Stratigraphic Units database, which is the national authority on stratigraphic names in Australia, the ASUD. The depth estimate peaks stored in EGGS can be visualized based on multiple attributes such as depth or the age surface they represent. On your left, the maps show the 220,000 points that were used in Northern Australia cover model, and on your right, the current coverage of depth estimates across Australia, including the current focus areas shown in purple. Although it looks like we have a good data coverage, if we zoom in, some of the constraining points are still widely spaced, and the traditional interpolation algorithm will only provide a fair result. So in this example, we extracted the Mesozoic depth estimates from EGGS, and we gridded them using an interpolation algorithm. Where we do have high density of points, we get a fairly good result, but it becomes less reliable away from these points. To address this, we developed a machine learning pipeline, UncoverML, to learn relationships between the depth estimates and other geological and geophysical datasets to refine predictions into areas where data is sparse. The results show that both models return similar predictions at the regional scale, but at smaller scale, you can see more variations in the machine learning model. In this example, because we used the probabilistic approach, we were also able to quantify the uncertainties of the model, in addition to improving the predictions compared to the interpolated model. For example, here, the green colors on the right indicate that the difference between the model and input data is less than 10 meters, whereas in red, mostly in the deepest areas, the error is greater than 200 meters. To date, we have progressed the Cenozoic surface at national scale and the Mesozoic surface at regional scale. Our initial tests suggest we need to develop a new set of covariates to improve the reliability of the results for deeper surfaces. So in parallel, we are also assessing a hybrid method where a combination of outputs between UncoverML and Loop3D could help solve this technical difficulty. So in conclusion, what are the next steps? So the objective of this work was to develop a first-order major unconformity depth maps with stratigraphy at continental scale to assess resource potential and reduce the risk of exploration undercover. To date, a series of tools, data infrastructure, and pre-competitive data acquisition programs have been successfully set up to achieve this goal. In this talk, I focused on cover modeling, but there are many other datasets developed under Exploring for the Future we could use as proxies to inform the subsurface geology and suggest sniffs of mineral systems. For example, surface geochemistry datasets are in development to map the characteristics of exposed rocks, soil, and water chemical signature that can be used as effective exploration tool in covered regions. We are working toward understanding the geological architecture at continental and lithospheric scales. So our aim is to progressively refine depth surfaces at geological periods level, but also expand the model in depth and include other data types to map deeper lithospheric discontinuities, such as the Moro or the lithosphere-asthenosphere boundary. Finally, we will progressively move from depth surfaces modeling to volumetric modeling to understand the link between geological, geochemical, and geophysical signatures. All these activities will help refine conceptual mineral system models by answering some of the key questions listed here on this slide. All the dataset, maps, and publication will be delivered via the portal and web services. So thank you very much for your attention, and please don't hesitate to reach out if you have any questions. Thank you.